So yesterday we told about classical mechanics. So the equations of motion or Lagrangian dt is your action. This L is a function of qi and qi dot. I have put qi because general variable, dynamical variable. Okay, it can be x1, x2, xyz for the first particle, for the second particle another xyz, for the third particle, etc. All of them put together is qi for me. And similarly, the time derivative of each one is qi dot. That's the only thing. So it's a generic label. It may be having one particle, it may be having many particles, it may be degrees of freedom which are associated with that. That's all that means. Now, given this, if I impose this condition delta S is equal to 0, then it will give me an equation which is called Euler equation. It is given by this. This is the equation which you will get by Euler equation. You are aware of it, right? This is what is called Euler equation, Euler Lagrangian equation. That is your equation of motion. That is the equation of motion. It is same as your Newton's laws written down, okay, with appropriate terms. For free particle, just for free particle, L is, or let me take L is half mx dot square minus half kx square. Okay. If I take this, and I will do this exercise only once for you, dl by dx dot is, from here it is mx dot. Is it visible what I am writing? Huh? Okay. So it's fine. Is it visible, that one? Is it sufficiently bold enough, or should I write it bigger? Okay. So that is simple. I have not done anything. M of mx dot square, if I differentiate with respect to x dot, I am going to get mx dot. It is 2 mx dot, x dot square is 2 mx dot, and half is there, you will cancel and get it. D by dt of that, d by dt of this, that is what you have here, is d by dt of this, which is mx double dot. Okay, double dot is two derivatives, d square x by dt square. Now what about the right hand side? Is equal to dl by dx here, and that is here minus half kx square. You differentiate with respect to x, you will get again kx. So this is equal to minus kx. So the equation of motion is mx double dot is equal to minus kx. That's all. You can even write this as x double dot is equal to minus k by m times x. You call this omega square is k by m. Then x double dot is equal to minus omega square x. This is the equation of motion for harmonic oscillator. If you have two oscillators of the same frequency, you will have one for y, one for z, whatever you want to have. This is the simple way in which everything is derived. Whether you have gravitational potential, you have spring constants like this, or any other problem, except one problem. And that is when you have, this is because here the force mx dot is double dot is the mass into acceleration. What is the force? Force is proportional to the displacement in the spring constant, right? That's a strain. Force is proportional to the strain which you are creating, and that is what kx is. And it is inverse, it actually towards that. It wants to bring it back. That's what I am written. I have not written very, very complicated. This law, which is called Hooke's law, is valid for most of the situation. That's what is the thing. Now, if all these things, when you have force is equal to g m by r square r unit vector. This is what you call the force between earth and the sun, okay, Newton's gravity force. The potential for that is gmm by r. It's only 1 by r. If you differentiate, gradient of 1 by r is 1 by r square times r unit vector. That's all, as simple as that. It's like 1 by x, if you differentiate, you will have 1 by x square minus 1 by x square. That's what you will have. So that's what I have written down. Now, if you do that, then this t minus v will give you the L will be half m r dot square minus gmm by r, where v is the potential. And if you do the same way, like differentiating with respect to r, differentiating with respect to x, y, z, etc., 3 coordinates, you will get the same thing. But differentiating with respect to x, y, z is very complicated, because that r is square root of x square plus y square plus z square. Now you have to differentiate 1 by x square plus y square plus z square with respect to x, with respect to y, with respect to z. So we prefer not to go through the Cartesian coordinates. We use what is called spherical polar coordinates. You have heard of spherical polar coordinates? It uses r theta phi. Okay, it uses r theta phi. In terms of r theta phi, it is very simple to differentiate. It's only 1 by r. The rest of the things do not play such a role. So that is what leads to, because the fact that action or Lagrangian does not depend on theta and does not depend on phi, give rise to that if you translate theta, nothing will happen. There is no theta dependence. If you translate that, nothing will happen. If you translate phi, nothing will happen. That is a symmetry. That is your symmetry, and that symmetry leads to the conservation of angular momentum. And that is what simplifies the problem in the case of this kind of a thing, like gravitational force. Okay? And that immediately gives rise to an equation r as a function of t and theta as a function of t. You don't have to worry about phi. The whole thing is in a plane, and that gives you the elliptical orbits will follow from this in very, very simple terms. I don't know whether you have done that, otherwise you should try to do it. Okay? That equation for ellipse in xy coordinate is something which you all know, x square by a square plus y square by b square is equal to 1. Do you know that? But if I ask you to what is that equation in terms of polar coordinates, spherical polar coordinates, anyone know that? Anyone? Do you know what is that equation for ellipse in spherical polar coordinates? What is the equation for circle in spherical polar coordinates? These are all the questions in interviews. When you don't have an answer for that, then there will be a problem. What is the equation for circle? You say x square plus y square is equal to r square, right? That's the equation. No, I want it in spherical coordinates or polar coordinates. What is it? R is equal to constant. R is equal to constant is the equation for a circle. What is the equation for an ellipse in polar coordinates? Anyone? 1 upon? Well, 1 minus epsilon cos theta or 1 plus epsilon cos theta is equal to what? R is equal to that. 1 by r is equal to 1 plus epsilon cos theta is what you will have. Okay, that is what you will have. This is the equation which you will have for ellipse. You should try to go through some of these things in some way. These are all analytic geometry, nothing to do with physics, right? It is nothing to do with physics, but that is what physics here tells you. So if you have an orbit of the earth around it, you perturb that orbit, that is, you have an ellipse, you make it wriggle like this, you find the action for that. That will be more than what you have computed for this. That's what the principle of action tells you. Okay? Anyhow, I will not go into that again and again. So this is basically the idea. So now there is one more thing which I mentioned yesterday, and that is what is the thing for QE plus V cross B. This is the Lorentz force. Okay, this is the Lorentz force. Okay, let us for the moment take even the case that E is independent of time, B is independent of time. There are constant electromagnetic fields. Okay, in that case, what is the Lagrangian which will give that? And I will give you the answer. What I expect you to do is, this calculation, what I have done here. This calculation, what I have done here, you should do it and probably consult and I will give you the answer. It is not very difficult. The answer is, Lagrangian is half mr dot square. This you expect, because when there is no electric field and magnetic field, the charged particle becomes free particle. So that's what you expect, kinetic energy. The only thing is, what is the extra term here? I will write it out. It is minus q V dot A plus or minus, or maybe minus q times phi. I have introduced two functions. I have introduced two functions, phi and A, and I have, for the benefit of the thing, I have assumed electric field is independent of time, magnetic field is also independent of time. They are there. Okay. Now, what is this A? That phi, electric field, is minus gradient of phi, and A, magnetic field, anyone? Del cross A. I hope you know this notation of gradient and curl. Okay, that's what it is. So from magnetic field is equal to del cross A, and electric field is equal to minus gradient of phi. If I have those definitions, then this Lagrangian here, if I do the same analysis like differentiating dl by dx dot, d by dt of dx dot, del by dx and dl by dx, if I do that, I will get that equation. Okay, you should try to do that calculation. It's only about 1 page. If you do it for x, it's enough, because what will happen to x will happen to y, what will happen to y will happen to z. So it's enough if you do one equation. There are 3 equations. Remember, there are 3 equations, 3 second order equations, but it is enough if you do one. The rest of them will be by symmetry, permutation. X goes to y, y goes to z. That's what will happen. Okay, you should try to do that. So this is what I was trying to remark yesterday. Now I will shift my gear and go to quantum mechanics. Okay. In quantum mechanics, there are 2 ways of giving quantum mechanics, actually many ways, but I will give you 2 ways for the benefit. One is Schrödinger equation. So there is a complex function psi, complex, of x, y, z. So I will generically write only x. When I write, it can be x, y, z. If it is a 3-dimensional problem, it is x comma y comma z. If it is 1-dimensional problem, it is psi of x. If it is 2-dimensional problem, it is psi of x comma y. Or any number of particles are there, each one of them you have to give that. So this is the wave function, what is called the wave function. Okay, it obeys, it depends on position and time. It depends on position and time. It is a wave, it gives rise to a wave equation, and that wave equation is called Schrödinger's wave equation. What is that equation? That equation is minus I h bar d psi by dt is equal to, okay, h bar square minus h bar square by 2m del square psi del square plus v of x y z, okay, psi. That is the equation which is called it's a wave equation. Have you heard of wave equations? Okay, wave equations describe some wave. What is the property of the wave? That wave, when it moves from, if it is a curve like this, after some distance it will have a wavelength and then frequency both. It will be described by wavelength and frequency. It can be a linear combination of frequency and waves. So it can be a linear combination, you need not assume. So it will be having a form like f of x minus vt. So it will be f of x minus vt or f of x plus vt. The wave can move in this direction or wave can move in this direction. So it is a kind of a wave equation like this, okay, wave equation like that. And so this is what came from whatever de Broglie said as the particle nature of, the wave nature of particles. Okay, if you remember the history, the photons, light, behaved like particles, waves, which was done in Young's double slit experiment. Have you done that? Young's double slit experiment or diffraction experiment, etc. That's what you expect from waves, right? Now, it happens even in water waves. The water waves also. In fact, the great interesting thing is the wave, when the light wave which is coming here in this direction, and there is a wall here, it will even go bend towards this thing. It will bend towards this. Okay, that's what the diffraction will tell you. Okay, diffraction around an edge. That's a property of the waves. In fact, if you all remember, I don't know, maybe you were kids at that time, in 2004 there was a tsunami which was coming, the wave was coming in the Bay of Bengal, from the Bay of Bengal, Indian Ocean, it was coming, and towards India it was coming. Near Kanyakumari there is a wall. Kanyakumari, this thing is a wall, and it was making a bend and going towards the Kerala side. So that's a property of the waves. Okay, waves do that. That's what they are supposed to do it, and they do interference, they do diffraction, etc. Particles, on the other hand, no, it goes straight, right? If I throw a stone, it will not bend like this. Well, nowadays, if you have a cricket ball, if I throw it in some way, the angular momentum and the air movement can be adjusted such that it goes like this. Okay, that's what the swing in cricket will happen, but that is due to more complicated phenomena. Particle tries to go only in the straight line, but that is not the property of the wave initially. So that's what is the problem which was there, but people proved that light has a wave-like property. But around 1900, suddenly it realized, if I want to explain my black body radiation and later photoelectric effect, etc., that the particle nature of light is needed. That was the concept which was there. Then there was a problem, well, if light behaves like wave and particle, what about electrons? Do they behave like that is the question, and the proposal was made, oh yeah, electrons also behave exactly like this. So they said that electrons behave like particles on Mondays, Wednesdays and Fridays, and the rest of the time it does the opposite. So something like that. There was a big confusion about this, and the whole thing was unified for both of them in this kind of a Schrödinger equation which is there. In the Schrödinger equation, we don't have an equation for photon. If at all, it is only our electromagnetic field equation. But we can describe an equation for light in relativistic context, quantum mechanical or quantum mechanical equation, which probably you will learn later. But as far as Schrödinger equation is concerned, it talks only particles with mass, some mass. Exactly like Newton's equation I mentioned, I asked you what is the Newton's laws for photon. Okay, F is equal to ma. What is the mass of photon? No, zero, I don't know. So that is a kind of a problem which was there, and the same problem will be there because Schrödinger equation is also for what you may call what probably Indumati taught you yesterday, relativity, and it is for non-relativistic context, non-relativistic situation. Okay, so this is your wave equation which you have for the thing. The psi depends on position and time. Now sometimes we make what is called the stationary state. The psi which I have written down, complex function, describes the state of the system. The system for us is a particle. At the moment it is a particle. So the state of the particle. In classical mechanics, I will say the particle has this position and this velocity, or this position and this momentum at this time. It will change. Currently it is at this point and it has the current momentum as this. If I know whatever forces acting on it, I know where the particle will be at a later time, and later momentum also what will be. Like for example, the earth, we know it is here with this velocity. We know after 2 months it will be some other place with position and momentum. That is what the classical mechanics will tell you. Okay? Classical mechanics will tell you, but in quantum mechanics we can talk about the state of the system in Schrödinger's thing is given by a wave function, okay, which is the position of. So what is it to do with where the electron is? That is the question I will come. So that is what is the thing, and we will be able to find out how the state changes if you use this equation. This is somewhat like Newton's equation if you want, okay, to describe how the state of the system changes. State of the system changes. The state is something called stationary state. The stationary state is something like, okay, the state of the system does not change with time. Okay, it is the same. So I have to tell how do I compute what is the nature of the system from the wave function, and that is given by what is called the probability density, which is mod psi square times some delta V, a volume. So in this region, take a small cube, you ask a question, what is the probability that the particle will be found in that cube? Okay? That probability is given by that expression. Okay? If I want to find out what is the probability it will be found in this cube, in this region, you have to do an integral. You have to find the integral of this quantity over that region. Now, if I do an integral for the whole volume, all the places, where will you find the electron in this whole, let us say, universe? You will find it somewhere. What is the probability to find the electron? It is 1. So what we will say is, this thing is 1. That is 1. The probability to find the particle, let me not call it electron, particle, because I didn't even put a charge for it. So that particle of mass m anywhere in the universe, okay, as far as this thing is concerned, if I do that integral, in any region if you do it, you will find it will have a probability which is less than 1. But if I do for the whole universe, it will be equal to 1, okay. That is what is the state. The state is not given by psi, it is actually given by psi square. That is the important thing. So that if I change my psi by e to the power I alpha times psi, I change it, psi going to psi prime is equal to e to the power some constant times psi. Okay. What is the state of the new thing, psi prime? It has the same probability density. Okay. As far as the probability density is concerned, it is the same. So this is the thing, the state is given by that mod psi square. That is the crucial point. Okay. Even though the equation is for psi. even though the equation is for psi. This is what you should remember. Okay, so that is the first part. So the second part, second way in which the quantum mechanics can be given is what Heisenberg did. This is Schrödinger's thing. What Heisenberg did was, okay, classical mechanics tell me there is a classical observable x, or let me call it q for the benefit, qx for example, and there is a momentum for the particle x and p, and that tells me the state of the classical mechanics, or the particle in classical mechanics. Okay? Correspondingly, he said that corresponding to x, there is an operator called x hat, there is an operator called x hat, and there is an operator called p hat, or px if you want. Okay? There are two operators in this case of one particle, x hat and p hat. Now, this object, the two operators which are there, okay, normally in classical mechanics, xp minus px is the same. It doesn't matter. It's all numbers. They are all what are called numbers. So that will be 0. Now he wants to take it to a next level. And the next level is they obey a relation. Generically it is called Heisenberg equation, commutator relation, and that where your h bar comes in. Your h bar comes here, your h bar comes here in these two things. Okay? Your h bar comes here and your h bar comes there. So this is the relation, first of all, for the operators x hat and p hat. Okay? Then you should know how the x hat and p hat, the operators tell you change with time. Okay? That change is generically is x hat dot is commutator of x hat with an operator called Hamiltonian, and similarly for p hat, which is what you had for Poisson brackets in terms of Poisson brackets, and that's what is there. Okay? That's what is needed for our thing here. Now, in all these things hereafter, the value of h bar is not playing any role, except is a number we need it. Okay? Unfortunately, in our levels of physics, we want to use, as long as it is not 0 but that's a constant value, we will associate a number 1. Okay? Number 1. For me, h bar is equal to 1. For me, the velocity of light, c, is equal to 1. Now, you may be wondering what the hell, c is equal to 1. Okay? It all depends on what is the unit you are using. It depends on what is the unit here. If you are using kilometer, if you are using meter, etc., then you have to tell me 3 lakh kilometers per second. Okay, that's what you should tell. Now, supposing I call 3 lakh kilometers as 1 unit. Okay, some 1 unit. Well, we can name it after anyone. For me, for my present time, I will name it myself. My Govindarajan or TRG is 3 lakh kilometers. Now, in my unit, what is the speed of light? 1 by 1, which is 1, right? So that's what is the thing. It is only what is the unit you are giving to measure, to tell you. Okay, the actual thing can be different. At some stage, when I compare with you, I have to ask, what is your unit? Are you using centigrade or Fahrenheit? Are you using centimeter or foot, inches, etc.? Those things will change. Depending on that number will change, the actual number. But we may be talking about 1 foot when you are there is 1 unit. It might be actually some 24 inches, or in terms of centimeters, 30 centimeters, etc. Okay? So this is a thing, the units, actual units can be different, but the number, you can fix some unit so that it is 1. H bar is 1, C is equal to 1. That's why I am not writing hereafter this, even though I have written here, I will remove all these things. For me, it is I times 1. Okay? Is that clear? Is the confusion sufficiently grounded? Yes?
It's going to
Okay.
We are used to say that psi is a state, right? Even when we are doing measurement and all. It's like the state psi will collapse to one of the eigenstates.
Yeah, yeah.
So,
okay, go ahead.
Like I'm little not clear with the terminology which you said for the probability it's
I'm
a
not
state.
using any collapsing now, as of now. I have not come to the idea of measurement as such. I'm only trying to tell what is the state.
Okay.
I'll find out the state is described by actually not psi, it is psi square.
Okay.
Okay? And the state will change with time. So the state which was here with some classical mechanics things which you had, when you want to describe it will change. Okay? Now I talk about the measurement and other issues slowly to the level, because it is a little more complex. The idea of measurement theory in quantum mechanics is far more than what Schrödinger imagined and what Heisenberg imagined. It's far more complicated. But for our purposes, we will try to do that. Okay? So this is basically the idea. So I'm only talking about the state is described by this. Okay. Now, what is the difference between this? This is what you may call as the Heisenberg picture, and that is what is called the Schrödinger picture. That is what is called the Schrödinger picture. I just want to give a simple trivial way in which the difference between them can be understood. Now first you can ask the question, I said these are all operators. These are all operators. Okay? These are all operators. There the wave function psi is there. Now the question is, these operators act on where? Operators should act on somewhere, right? So that action, it acts on, generally the name is Hilbert space, vectors on a Hilbert space or Hilbert space. We need not worry into too much details of Hilbert space, except that I have some vector space, okay? I have some vector space, and vector space, probably you know, there are vectors in 2 dimensions and 3 dimensions and any number, and on that vector space there are operators. So I will give you a simple example of that. So for example, I can have a 2-dimensional vector space x comma y or x1 x2. This is a vector space. Any vector is specified, some vector here, let me write a1 a2. It is what you will write a1i a2j, right, unit vectors, etc. Or I will be writing this as a column vector. As a column vector, that's my vector space. Okay? Now if I want to find the length of the vector, we will say it is a1 square plus a2 square, which is something like, you take the various ways you can write a1 a2 as a row and as a column, or if you have another vector b1 b2, you can take the dot product also. You can take the length of the vector like this. This is what you have, right? So this is what is required as a starting point, vector space. It can be 2-dimensional vector space, it can be 3-dimensional vector space, and it can be 4-dimensional vector space, because I didn't specify there. Unfortunately, for this object which you have here, the vector space which you want has to be infinite dimensional. Okay, it has to be infinite dimensional. Why is it so? Because this is my vector, and in this vector I can do 2 things. I can take the vector and change it to another vector. a1 a2 goes to a1 prime a2 prime. Okay, a1 a2 goes to a1 prime a2 prime. What is it you have done? You have taken the vector and moved to this thing. So that vector, as a function of time, it can go from this time. You can even take it as a curve, okay, as a function of time. That's what has happened. Now what is it I will say? I have rotated the vector from a1 a2 to a1 prime a2 prime. So that operation is a rotation which I have done in this vector space. So that operator is a rotator. rotation which I have done. That is one thing here. So the state, the vector is a starting point with a vector state, goes to another vector, which is what has happened. Okay, that's what has happened. Now I can talk about this thing in two ways. I can take the vector and move this thing, which means my frame, the coordinate system remains a constant, does not change, but my vector goes from one to another. Okay, that is one way of saying that the vector has done this. Another way of saying that is the vector remains the same, my coordinate system has rotated, right? My coordinate system has rotated. So the operator which does the rotation is changing with time. You can rotate this whole xy coordinates like this. Whereas the other way of saying is my state remains the same, but the state has changed with time, but operator has not changed. Operator has not changed with time, but it's only the state, the vector has changed with time. And that is what Schrödinger gave. He is having that psi is a vector in an infinite dimensional space. It is a vector in an infinite dimensional space and it is changing with time. For Heisenberg, that infinite dimensional state vector remains the same. The operator, the rotator, changes with time. And how does it change with time is given by this. Is given by this. Okay? So this is the equation for how the operators change with time and how the state changes with time. One way of saying is what Schrödinger said, another way of saying the same thing is what Heisenberg did. So this is what in quantum mechanics they will call as Schrödinger picture versus Heisenberg picture. Is as simple as that. Okay? Schrödinger picture versus Heisenberg picture. In vector things we know this as active transformation and passive transformation. We call it active and passive transformation. Passive is vector remains the same, but the whole car is thing is rotated. That's what is the thing. Okay? So that is the only difference and both are one and the same. Now I mentioned in these things, I gave the example with 2 dimensions here. Okay? Why 2 dimensions? Because I can't have 1-dimensional vectors, then it is only a number. Then x hat with p hat, if it is a 1-dimensional thing, it will simply, vector space, it will only commute. X hat p hat should be equal to p hat x hat. Now, the fact that if you have written like this, okay, as operators in some vector space, that x hat p hat has to be necessarily infinite dimensional. It has to be necessarily infinite dimensional. Now why is it so? And that is because if they are numbers, they will commute. But if I have 2 matrices A and B, because after all what I am doing is when I go to operator, I make them as matrix. That's why it is called matrix mechanics, because numbers will not do. So I am going to associate a matrix, and I will tell you what that matrix is also when I do the harmonic oscillator. That matrix A and B, something like A and B, if commutator is AB minus BA. You know the commutator of 2 matrices, right? AB minus BA. Let us take any finite dimensional matrices A and B. Okay? Now, if I find the trace of the commutator AB, you know what is the trace of a matrix? It simply add all the diagonal terms. You add all the diagonal terms. If you add all the diagonal terms, you will get the trace of that matrix. So I find the trace of AB, which is trace of this object. Okay, trace of this. So A is a matrix, B is a matrix. You multiply it out and find out the trace. Okay, any finite 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, 10 by 10 matrix, 100 by 100 matrix, million by million matrix, trillion by trillion matrix, any matrix you write A and B, if you find the commutator A and B, the trace of that will be always 0. It will be simply 0, right? So try to prove it. You know matrix algebra, matrices, you know about matrices, you find out Aij, you call it matrix, it doesn't matter how Aij can be from 1 to n, okay. From there you can prove trace AB commutator has to be 0, okay, has to be 0. But if the matrices are finite dimensional matrices, is the relation AB commutator trace is 0, is it true if the matrices are infinite dimensional? Answer is it is not true. And that is the reason here I have my operator which is x hat p hat, and I find the trace of this, I find the trace of that, you expect it to be 0. You expect it to be 0. But what is it you have written on the right hand side? You have written it as trace of IH bar. Now what is that matrix which I have written there? Identity matrix. It is only 1, 1, 1, 1, 1 everywhere. Okay, 1, 1, 1 everywhere. So the trace of that is the dimension of the matrix. Trace of IH bar is n. What is the d by d matrix? It is d times. If it is 2 by 2 matrix, 2 times. If it is 5 by 5, it is 5 times. That's what you expect. Okay? So you expect on the right hand side that number is not 0. It is not 0. Whereas you expect this to be 0 if it is a finite dimensional matrix. Okay? Is there any question? Yes?
Like even if it's finite dimensional, we say the trace is 0, the trace comes out to be 0. Why is that a problem? Why is trace?
But the left hand side is 0 and right hand side is non-zero.
No sir, I mean if x cap and p cap are considered to be finite dimensional
Okay.
vectors, then
that relation cannot be, you cannot find a vector space for which this is a finite dimensional matrices, whereas because this is not 0 and this is 0.
I see.
And it is possible to find only if the matrix is, it is an infinite dimensional matrix.
Thank you.
Okay, that's what is it. It's possible to find. I'll tell you what is it infinite dimensional space is. Okay, and in fact that infinite dimensional space you already know it. I don't know. It's very simple. Unfortunately, these are all something which you know. Have you been taught Fourier series? You have some idea about Fourier series, and that's what I'm going to do. So this is what is the thing. So what is that vector space? That vector space, what you want to have is a special vector space of functions. If you have psi as a function of x, let us say 1 dimension, psi as a function of x, right, 1 dimension. It's a 1 dimensional space, the particle is in 1 dimension. Psi as a function of x, now you have given this relation, this thing, mod psi square, psi of x, it's an arbitrary function in 1 dimension. So let me write down, this is my 1 dimension x, this is the psi, so it can be like this, some function I have drawn for your benefit, okay. But it should be such that this is equal to one. It has to be 1. Now, for example, if I give a function e sin x or e power ix, e power x, I give a function e power x. Is it a good function? Will it obey psi x whole square integral is 1? No, it will not, because it will be infinity. Or if I give you a function simply x square dx between minus infinity to plus infinity, x square dx, is it finite? No, it cannot be that. Now can you tell me a function which you integrate will give me some number? If you have that number, you can put that number below and then think. Can you give me a function? Yes, so this is what you know, e power minus x square, e power minus x square, if you square it, it will be x square by 2 to start with. If you square it, you will have e power minus x square integral dx from minus infinity to plus infinity. So the area of this curve e power minus x square on the x-axis, along with the x-axis, is only a finite number. It is only a finite number, so it is a good function. Okay, such functions are called square integrable functions. They are called square integrable functions. Okay, so I will give you some more functions. For example, in this thing, you can have something like this. You can even have like this. It becomes 0 far away. It has to become 0 far away. Any function which you have, it has to become far away. Whether when you go to infinity on the x-axis plus infinity or minus it has to go to 0. Right? The question is how fast it goes to 0. How fast it goes to 0. Right? That is very crucial. Okay? For example, a function like 1 by x square plus 1, integral from dx from minus infinity to plus infinity. It goes sufficiently fast to 0 at infinity both sides. So it's a good function. So there are several functions which you can have, okay, which are called square integrable functions. And that is a class of functions which you should use. That class of functions are called square integrable functions, which are called L2 functions. There is a name for that. This is the mathematical way in which we write. Square integral R there stand for real numbers from minus infinity to plus infinity. That is the place where you are having the function minus one dimension. I am not doing anything more. You can do it to 2, 3, any dimensions. Okay? L2 is simply stating that the function is square integrable. You take the function, square it, integrate it from minus infinity to plus infinity. Are you getting a finite number? If you get a finite number, you divide by that number and call that as a new function. Okay? And that will be equal to 1. So only those functions are allowed in Schrödinger picture. Okay, it is allowed in the Schrödinger picture. Now those functions which you have here is a vector space, and the vector space is infinite dimensional. It is a vector space, infinite dimensional vector space, and that is all that is required. Okay, so that infinite dimensional vector space in which operators x hat and p hat are there. So these things, I am going to erase them. This relation which you have here, I have to see it as x hat, p hat acting on psi of x, which is square integrable function, produces for me I h bar psi of x. That is the relation which you want. Okay? So I can have some nice representation for the operator x hat and p hat. One such representation is x hat on any function f of x is equal to x f of x. Simply multiplies it. X hat acting on f of x gives me simply x f of x. X hat is an operator on the left hand side. On the right hand side, it is only a number in that coordinate system. You should distinguish between hat and unhatted, okay? And similarly, what is p hat? P hat f of x is minus I h bar d psi by df by dx. df by dx. P hat acting on f of x is only differentiates this with a constant which is I h bar and gives you that answer. So that's what you are having. What does it mean? X hat is an operator. So f x is a vector. As I told you, it is a square integrable function. It is a vector in some infinite dimensional space. And then x hat acting on that will give you a new function, x f of x. Similarly, p hat acting on that will give you a new function, differentiate. So it gives you a new function. So psi has become psi prime, or f has become f prime. Similarly, f has become df by dx, it has become a new function. That's what the vectors do. The vectors change from one value to another vector, right? It can be a1, a2. Even if it is infinite dimensional, I can write an in-column vector. I can write a column vector, I'm going to do it, which is infinite dimensional, starts from 0 to infinity, okay? That is the kind of functions, and all the square integrable functions are labeled like this. That's what x hat does, p hat does. So the difference between Schrödinger picture and Heisenberg picture is this object psi of x changes with time given by Schrödinger equation. Okay? That is what the state changes with time. Now Heisenberg picture is this doesn't change with time, these things change with time. X hat, this operator and this operator changes with time. So Heisenberg picture is only x hat as an operator changes with time, p hat as an operator changes with time, psi x always remains the same. Whereas in Schrödinger picture, it is psi which changes with time, x hat does not change, p hat does not change with time. But they are only equivalent way of saying the same thing. They are all equivalent way of saying the thing. So these two representations, I will call it a new term. The term is called these two representation, Heisenberg picture and this thing are equivalent. They are one and the same. They tell the same physics. Okay? That is the beauty of that. Okay? Now comes the measurement issues. Minimally I will tell you. So the important thing is, if I measure the position, I am given a state, psi of x. I am given a state. I want to know if I measure position of that particle, where is it? Okay? There will have several places, because it has a probability. If it has a probability, then it can be found here, sometimes it can be found here, it can be this thing, etc. So there is something called expectation value, which is simply take the x hat, that psi of x, let me write, you find this quantity is equal to psi star x hat psi dx. You find this quantity. Earlier I found only psi star psi, right? I integrated psi star psi. Now integrate psi star x psi. Okay, so it's a new function which has come now. Xi is a new function. So find this thing, find this number that will tell me the expectation value of this operator, of this thing. It is a number. Finally, it is a number. What you meant by this, when you try to see where the particle is, very large number of time it will be found at that value. It will be distributed. The maximum number of this will be here. But so if I try to find the particle, it will be it will have some value like this. This is the maximum here. But you will find at different places. at different times. So this is what you have here, but this will be distributed, it will be distributed from here to here, okay. The expectation value tells you where you will find, let us say, a large number of times, okay, maximum number of times if you want. But what is required for us is not this quantity, what you need is x hat square expectation value minus x expectation value square. This is what is called delta x. What is the expectation value? Okay, this is how far, if you have, the point is it is distributed from here to here like this, you will find that this is the region within which most of the time it will be found. It is a small region within which it will be found, okay. That is the number, okay. There is a maximum value and within, so it can be found, say at this point, within some 1 foot from here, 1 foot from here, it will be found all the time. In fact, very large number of times, 99.9%. So that is what you call as a expectation or uncertainty about this x hat when you do the so-called measurement. When you do the so-called measurement, that's what you need. Now this number is always positive. X hat square minus x square average is always positive. It's easy to prove. It's almost like the theorem which you have, what is called the theorem in sum of two sides of a triangle is always greater than the third side. That's what it is. This theorem is only that much, that it is always, this minus that is always positive, okay. The sum of two sides of a triangle will be equal to the third side if they don't form a triangle, but it is only a straight line, okay. That's what is it. If you have, so that's the kind of theorem which you have here, and that is what you have here, okay. So this is a very, very brief introduction to Heisenberg and this thing, but now I should go to some problems. Okay, a simple exercise. I am going to do a simple exercise, and that also is what is not normally taught in colleges, etc., as a first starting point. First, you need what is called the stationary state. I am going to assume psi is e to the power I e t. I am going to take, I should write e power I e t by h bar, okay, because that's the dimension. Energy times time is the dimension of h bar. So I am going to assume h bar is 1, so I am not writing that h bar, okay, times some phi. Let me write this phi, let me write it as phi. This is depending on x and this is depending on the time. I have separated the time dependence and position dependence by this division. Now you can ask the question, if you have such a psi, then if you substitute here, I will call this as h Hamiltonian, Hamiltonian. Your equation will become h phi is equal to e phi. If you substitute it, because I have here, let me remove this h bar here. I have removed this h bar here, and this is 1 here. I have removed this. Substitute it, you will find that this differentiation with respect to time will bring a factor of I e. There is a minus I e that makes it e phi here, okay, and the right hand side is only h phi, okay. That's what is a very simple differentiation. This is called time independent Schrödinger equation. Time independent Schrödinger equation. And h hat, which I have written down, is, as I told you, it is only operator. differential operators. P hat del square is nothing but P square, P hat square. Okay. So this is an operator. This is an operator. I can even put a hat over it. Phi is a vector in one dimension. Square integrable functions in one dimension. Phi of x is an arbitrary function. But only thing is you should make sure that phi x integral square integral is 1. So it is a square integrable function. H acting on that should give me the same function with this multiplied by some number. This is like a matrix equation. Okay, a matrix equation which you have here, some matrix A and then some vector V gives you lambda times V. Okay, this is what called eigenvalue equation, and there may be many eigenvalues. There may be many vectors which will satisfy that. So find out all of them. So that is what is that equation tells you. Now an arbitrary function psi, supposing this is some ei and phi I, an arbitrary function psi can be written as sigma ai phi I. Okay, you can write it as that. Now you can ask the question, this is a function again only of x, this is a function of x. Okay. Now what is the time development of this function is, they will all go by e to the power I e I t. That is what it will do. Each one will evolve with time only e power I e t. So an arbitrary function will evolve, each frequency will evolve in different times. So you will have the whole function evolving in time in different ways. That is what is happening. Okay, is that clear? If it is not clear, please do ask me. So you can express Hamiltonian, what we call the H as an operator, find the eigenfunctions of that. You can express a linear combination of that, and if it is an eigenfunction, that phi, it will evolve with only e to the power I e t. But if it is a combination of two eigenfunctions, phi 1 and phi 2 with different eigenvalues, their the time development is e power I e1 t and e power I e t. Two different time energies. So they will evolve differently. So you will find an arbitrary function will evolve nicely obeying the Schrödinger equation, because Schrödinger equation is a linear equation and there is no problem in that. You can always add solution. The beauty of Schrödinger equation is that is a linear equation. You can always find a general solution by adding solutions of that equation. Okay, that is what is it. If it is a non-linear equation, you cannot do that. Okay, that is what is the problem. You know the difference between linear and non-linear equations? Linear equation is, if I had something like instead of this, there is the psi appears here linearly, there is only one power. Supposing I had one psi square also appearing there, then it will become non-linear. Okay, that is the idea. Okay. So given this, let me try to solve this thing for a simple case, which is what all quantum mechanics classes talk about. Which is called particle in a box. Okay, particle in a box. I didn't tell what is that V of x. Now I am going to tell you what is the V of x. Okay, I am going to tell you what is that V of x is. The particle in a box, well, a box is this kind of room. The room is locked. You cannot run away, right? But inside the room you are free. You can go anywhere. It is a free particle inside this room, but once you go to the wall, you are hit by a wall which will push you back. That wall is infinite potential. You cannot cross the wall. So I am going to give you that picture. This is in one dimension. The V, this is my origin. This is a point which is, I call it as length of that box is 1 unit. Length of the box is 1 unit. And this is 0 potential. V is 0 here. and V is infinity here. V is infinity here. Okay, it's like this room. You cannot get away. Till I open the door, you cannot go away, right? So this is the thing, there is an infinite potential outside, zero potential here. You are free to do anything you have. You can run, okay? You can run here, but you are a free particle here. And outside you cannot go. It's like a jail. A box, particle in a box is a particle is in a jail, and the jail is here. So I am going to solve this equation. So since V is 0, the Hamiltonian here is minus 1 by 2m d square psi by dx square. This is my Hamiltonian. It's only that, there is no potential. Now outside it is minus d square by dx square 1 by 2m plus V, which is infinity, infinite potential. Since it is infinite potential, you cannot find the particle outside. You say the particle cannot be found outside. So it is 0. The probability will be 0, so the function will be 0. So you expect the psi to be 0 here and everywhere. Psi is 0 here and psi is 0 here. Okay, the function is 0 up to that point. So at that point it has to be 0. At this point, what is the value? Okay, at this point, as you come here, as you come there. So that is a $1 million question. Okay, is it 0? So we will take it as 0 because I assume my function is continuous. Okay, I will have the function which is continuous. It can be like this, 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 etc. But inside it is some function and reaches 0 value at the end points. So that's what we call as the boundary conditions. So the condition is psi is equal to 0 at x is equal to 0 and x is equal to 1. At these 2 points it has to be 0. At these 2 points it has to be 0. Okay, outside it has to be 0, there is no problem. Okay, that, and it should be square integrable. So I have to solve this equation, and I am going to assume for the moment my mass of the particle is also 1. Okay, it does not matter whatever particle is there, as long as it is not 0. So it is minus 1 by 2 d square psi by dx square is E psi, or let me write it as 2E here with a minus sign. Okay, I am going to solve this equation. I am going to solve this equation. Now this is a very, very simple problem. This is a very, very simple problem, and the solution is, because it is like your harmonic oscillator problem. Harmonic oscillator d square psi by dx square is some constant time minus x, minus the same function. If you have some function this kind, d square psi by dx, d square f is minus omega square f. If I write like this, the solution is sin x and cos x. They are the solutions, right? Sin omega x and cos omega x. That's a kind of thing which we'll have here. So like that, I have this function. So let me call it as minus some lambda square. So the solution is sin lambda x plus cos lambda x. A times this, B times this. This is a solution which we'll have here. Okay. Now at x is equal to 0, you want the function to be 0. And sin lambda x is 0 automatically. Sin lambda x is 0 here. This will be 0 here. psi at 0 is a sin lambda x is 0, this is 0, plus b cos lambda x, but at x is equal to 0, cos 0 is 1. So, I will have only b here, this is b, and that should be 0. We expect it to be 0. So, b is 0. So, your function is only sin a, psi solution is a sin lambda x. That is a function. Okay? That I have applied only one boundary condition. I have to apply the other boundary condition. Okay? I have to apply the other boundary condition. Now, at x is equal to 1, x is equal to 1, which means that sin lambda, okay, it should be 0. Now, it can be 0, sin lambda can be 0 if lambda is n pi, right, if lambda is n pi, right. So, the solution is, psi is equal to a sin n pi x. And let me call it as psi n here. For each value of n, okay, for each value of n, if n is 0, there is nothing, the function is 0, we do not want it. N is equal to 1, there is a solution. N is equal to 2, there is a solution. N is equal to 3, there is a solution. For all values of n, there is a solution. N is equal to -1 also is a solution, -2 also is a solution, etc. So, these are the solutions. A general solution is, what is the eigenvalue? Which means I have to differentiate that, d square by dx square. Okay? If I differentiate that, I will have n square pi square. If I differentiate that, it will be n square pi square. So, the eigenvalues are n square pi square, and the solution is sin n pi x. An arbitrary solution is a linear combination of that. An arbitrary, so let me try to plot some of these functions. I do not need this thing, so I will try to. So, this is my 0 and 1. When n is equal to 1, it is sin pi x, right, sin pi x. So, it is a function like this. Okay, it is a function like that. For n is equal to 2, sin 2 pi x. So, it will be like this function. For n is equal to 3, that will be very simple. It will have like this. So, you can have different solutions, which are what you all know in if you have done sound and other things. If I give you a string, I hold a string and she holds a string, one end. If I try to do this, there will be a wave. And standing modes, what we call standing modes, they are the standing modes. An arbitrary combination of standing mode is a solution for Schrödinger equation in this case. They all obey. At x is equal to 0, it is 0, and x is equal to 1, it is 0, and standing modes are there. Is that clear? That is what is called the particle in a box. Particle in a box is only that much, as simple as that. You have done the quantum mechanics. First, quantum mechanics. Unfortunately, even in this there are some complications, and that complication is not what is probably not there in many books, and I am going to give one of them, because next 10:47, by 11 I want to finish. So, I will tell you what is that. Okay? Is there any question till now? Please ask me, because I am going to give you some interesting thing Now you have learnt from me, you can go and bother your teacher, your school, college, or wherever you have. Okay? An arbitrary function is psi is an sine n pi x, right? I don't know whether you have done Fourier series. Have you done Fourier series? What I'm doing is only Fourier series. There's nothing. I'm doing an arbitrary function. I'm doing, this is my x-axis, between 0 and 1, there is some function here. I write like this. Let me write something like, some function like that. Okay? And it is periodic. I repeat it again and again. Okay, which means I take the same function, do the same camel diagram. It's a periodic function. Okay, I can express my periodic function with the period 2 pi, with the period pi, this thing, in terms of sine series. That's what I have done. What I am doing is only take the Fourier series example and using it here. Standing modes are only that much. Okay. So all the other things are not there. So the other camels are not there. So you have to remove them. It is 0 here. You have to remove them. You have to remove them. You have to remove all of them. Everywhere it is 0. Everywhere is 0. Okay. If I give you such a function, you can always expand it in Fourier series. As simple as that, right? Is there any questions so far? Okay. So this is some function. So any function here is this thing, and the eigenfunctions are assigned this thing. The eigenvalues are n square pi square, n square pi square. Okay. Now if you have an eigenfunction, if you have some eigenfunction h psi n is En psi n. If I try to find out for psi n the expectation value for h, if I try to find for this, okay, the expectation value for that, okay, it is very simple. It is going to be, what is it going to be? H acting on psi n is En psi n. En is a number, you can pull it out, and psi n star psi n is 1, integral is 1. So the answer is En. The answer is En. Expectation value of Hamiltonian in the eigenstate is simply the energy eigenvalue. Now, what about this quantity? H square. What about this quantity? What about that quantity? Again, H acting on psi n is En psi n. Again, H acts on again the same psi n. So it will be En square, right? It will be En square. So this will be En square. Whatever power you take here, H cube, H to the 10, power 10, etc., En to the power 10, as long as it is eigenstate of psi n, psi is what is there, okay. So this is the first thing. So now I am going to find out H square average minus H average square, this quantity, okay, for the pure eigenstate. For eigenstates, for this told me that H square average is En square if it is eigenstate. H average is En, the square of that is again En square. So this is 0 if psi is equal to eigenstate. If it is an eigenstate, the answer is 0. If it is an eigenstate, the answer is 0. If it is not an eigenstate, a linear combination of that, it will not be 0, it will be always positive. Okay, that's an important point. Okay, I am reaching my punchline. Okay, now I am going to give you a function which obeys the boundary conditions, and I am going to, so since it is not an eigenfunction, it is not an eigenfunction, it is a very simple function. I am going to ask you to find out by afternoon or tomorrow afternoon, I will be here for tomorrow afternoon. Till then, find out the same quantity, h square average minus this. This is what you call as the delta E square. Okay, I will let me give the function. The function is psi is equal to x into x minus 1. Is it square integrable? It is 0 outside, I have to only integrate x square. Let me find the norm factor, integral. So this is x square minus x. So psi square is x square into x minus 1 whole square. Integral of this is what I should find out. And I have to integrate this only between 0 and 1. Everywhere else it is 0. So you don't have to do anything. You have to integrate it from 0 to 1. You find it from 0 to 1. Okay? It will give you a number. It is not very difficult. You can expand that x minus 1 whole square as x square minus 2x plus 1 and multiply the whole thing by x square. So any x power n integral is x power n plus 1 by n plus 1. That integral is very simple. You substitute the limits 0 and 1 and get the answer. So that's a simple first exercise. Find the factor. So let me call that number what you get as n. Let me call that number as n. I want my eigenfunctions to be normalized, which means I should take psi as 1 by square root of n. If I take it as square root of n, the integral will give you n and denominator will also be n. They will cancel out and answer is 1. That is what is called normalization of the vector. Normalization of the vector. Okay? So apart from that n, it is only x into x minus 1. At x is equal to 0, that function is 0. At x is equal to 1, it is again 0. But unfortunately, it is not sin n pi x. It is not sin n pi x. So it is not an eigen function. It is not an eigenstate. So it will have a combination of eigenstates. It will be several combinations of eigenstates. It will have infinite number of them also, possibility. Because this is the thing, Fourier series. Okay? Find out this quantity. Okay, find out that quantity. Actually, differentiation is very simple because x square minus x, you can easily d square by dx square, you can differentiate. That's not difficult. And that's where my punchline is also there. Differentiation is fine, you can do it. Okay, you will find, get me the answer by either today afternoon or tomorrow. Okay, and this is the first exercise which I wanted to do. And it also has some subtle thing which is not, up to this people will do, all books, textbooks, everyone does that sin n pi x by L. They will have not 0 to 1, it will have 0 to L. They will have 0 to A, or somebody will have minus L to plus L. All those things are fine. They are only trivial changes. 0 to 1 is fine. But after that they will get the eigenfunctions and then expand it and then do that, well, things, etc., explain it. But some complication which arises is the thing which is there. Last 3 minutes I want to spend something about this again. This is my box, V is 0 and V is equal to infinity here. V is equal to infinity here. What is it I said? My function, okay, my function psi of x is continuous function, right? There is a subtle thing here. This function is 0 here, it may be like this and like this, right? That is a continuous function. There is a continuity there, okay? But it is not smooth function. Why is it not smooth? If I find the derivative of the function in this place, as I go here, it is 0. The derivative is 0 as you approach that wall. But the derivative of this is like this. Derivative, as you know, is a tangent. Derivative is nothing but tangent. The derivative here will be like this. The derivative here will be like this. There is a tangent here and there is a tangent there. So that's why you don't call it a smooth function, but you say it is continuous function. The continuous function is the value you don't have, it doesn't jump there, okay? A non-continuous function will be like this. Okay, let me draw for you. Here, a non-continuous function is 0 here and 0 here. Okay, it goes to this value. If you want, after reaching this here, it goes to this value. And then maybe you can even put some wriggles here, right? That's a non-continuous function. 1 more minute, I'll finish. 1 more minute. I am maintaining my time. So this is the thing. That's a non-continuous function. The one which is there is a continuous function. The derivative is discontinuous. The derivative is discontinuous. So in quantum mechanics, you can ask the question, should the wave function be a continuous function? Should it be a smooth function, differentiable function, at what level you want? Okay, that is the question you can ask. You should go beyond what is there in textbooks. In many textbooks, they will say it should be smooth function. Everything will be smooth, etc. Because that's all they know. Okay? But answer is, now we have given a function here which is not smooth, it is continuous. It is continuous but not smooth. That is because my function is 0 beyond that wall, x is equal to 1 and beyond. It is x is equal to 0 and beyond, but it is non-zero only here. Is it allowed? That is the question. And the answer is yes, it is allowed. Because what is it you are trying to do? You are trying to solve a differential equation where the differential equation is like this. You are trying to solve this equation. That V of x which you have written is a potential which you are giving. From outside I am creating that potential, like this wall, etc. Is that V of x, is it a continuous function? It is not a continuous function, because here the potential is 0, outside it suddenly becomes infinity. Outside it becomes infinity. So when the potential, this differential equation here is that this is discontinuous, so you expect d square psi by dx square also should be discontinuous, otherwise how can you match? Okay. So d square psi by dx square should be discontinuous, which means d psi by dx can also be discontinuous. That can be there. Okay, that kind of a thing which is possible. So the smoothness is out of question. Now you can ask the next question, should it be continuous? The next question, should it be continuous? Are there other things which are allowed? Now I give you another boundary condition for this problem. Psi is 0, psi 1, let us say it is 1, well some number 1, not 0. Okay? What kind of thing is that? Okay? Now the function outside it is 0. Outside it is 0. It is 0 here and it is 1 here, 1 here. So the function is discontinuous. The function is discontinuous. Is it allowed? Is a question. Is there a problem with that? Is a question. Okay? And the interesting thing is now this function which I have given, let us say a function like this. The function is discontinuous because it jumps from here to here, it jumps from here to here, but the derivative is continuous. The derivative is continuous. Now earlier derivative was discontinuous, but the function was, but this is the opposite. So the question is, what is the one which you want? Sorry. What is the one which you want? Okay? Is it allowed? That's the question. Now actually you will find this is also allowed. It is equivalent to saying the particle goes and hits the wall, with momentum it comes back. Okay? With momentum it comes back. So the probability of finding the particle on very close to the wall is not 0, because it goes and hits and comes back. Okay, that's not 0. Whereas in the previous case, the probability of finding the particle very close to the wall is 0 because it is a sign function. Here it is not 0, non-zero value. Again, you can ask a question, if I have such a function, if I have this function and here, can I expand it in Fourier series? Okay, can I expand it in Fourier series? Answer is yes, this is the kind of function. That's also allowed. This kind of functions can be expanded in Fourier series, right? It's periodic. It's periodic. It's periodic and it is allowed. So this is a mystery that is allowing in the Fourier series, and that happens precisely in quantum mechanical problems also. Particle in a box, and try to work out that quantity, and more subtle things about this. Even in the very simplest problem, I will tell either today or tomorrow during tutorials, either today afternoon or tomorrow. I will probably join the students. Okay? This is basically the idea. Next one I am going to do harmonic oscillator, and I will do hydrogen atom angular momentum, from where I will jump to angular momentum. Hopefully by tomorrow I will finish up to angular momentum. Next 2 days will be time independent perturbation theory and time dependent perturbation theory, to the extent I can finish. Okay? Thank you. Now if you have any question, you can ask me. I am available here, and also do you have any questions?
Sir, sorry. So I think using that equation, if we don't assume psi to be continuous, we can, I think, prove that energy will come out to be negative from there. So minus d2 psi by dx2. Let's say at 0, around 0 we look at some epsilon range within 0. If we integrate that equation, so minus...
That's no problem. You will minus d square by dx square, that function operator. Which
I'm saying if psi is not continuous.
Even then, it's always positive. Because there is a very simple result. If I give you a matrix A, it will have positive and negative eigenvalues. But let us say all are real eigenvalues. It will have real eigenvalues, but positive and thing. Square of that, it will be always positive. So there is no negative thing possible. That minus d square by dx square is nothing but square of that minus I d by dx.
Yes.
So even if momentum has both positive and negative values, the square of that is positive definite.
I see. No, so my
You
question.
just give me one function, simple, take same function,
Right.
and even you take eigenfunction,
Right.
okay, not continuous, it's continuous, or if you want you could take that other function, cos if you want, and find out that value. You will not find it to be negative, okay. Other questions? So this idea about continuity of these things are not usually dealt with in many of the quantum mechanics classes, first time, etc. Because it is a little complicated. But this example of that function which I have given you, this function x into x minus 1 satisfies your boundary conditions, and even that provides some nice example of something nice to happen. Okay, be careful.